Hello. And we're live as everyone starts to kind of come in. I'm so happy that you guys can be here. If you're new to the Q&A, welcome. So happy you can be here this Sunday. What I do is in the beginning, I talk a little bit. I catch you guys up on what in the world I am doing, whether what new video I have up or any other resources I'm currently working for you guys for. Now, and then obviously once it hits 12 o'clock, we have like a little less than 3 minutes, a little less than 3 minutes, we'll start the Q&A. And of course, if you guys have specific questions, that really helps me as well. Now, what I wanted to talk to you guys about was last time I discussed a workshop that I was working on. So I'm doing a Lewis structure workshop that's already been pre-recorded, and it is designed beautifully, I would have to say, since I did design it. I worked really hard on this workshop to help you guys understand the concept of Lewis structures and be able to pretty much just ace your exam, because I know how difficult Lewis structures can be and just the concept itself. So I am doing a pre-sale on it. And what a pre-sale means, it means you get it for half off or a really discounted price in the very beginning. So it's only $10, and I'll be placing the link in the chat. Right now, it's only $10. It's a workshop on Lewis structures, on seriously everything you have to know. That's including how to draw Lewis structures, how to find valence electrons, polarity, all the different types of geometry, hybridization, resonance, formal charges. The list goes on. And it has a ridiculous amount of examples to really make sure that you get the concept down. So like I said, right now it is on pre-sale. What that means it's half off. I don't know how long I'm going to have that be half off. It's $10 at this moment, and later on it will go back to the original price of $20. But I believe either for up until this week or maybe in 2 weeks, I will change the price to the full amount, which is $20. So this is over 2 hours worth of just teaching and tutoring. I'd say the quality, of course, is really good. And it also comes with notes that I've made personally for you guys. I know how difficult a chemistry book can look like, and it isn't tailored to students. It's mostly for other people who understand chemistry. So I've designed these notes for people who don't, completely understand chemistry, that you're new to chemistry and you're learning it. And that's how notes, I feel like, should be. So that's what I've been doing. I've been working on this workshop really hard. So I definitely recommend to check it out. And like I said, it's on pre-sale right now. I don't know how long it's going to be on pre-sale for. It's just $10, and it will help you so much with Lewis structures. If at this moment you're not on Lewis structures just yet, but you see on your syllabus that you will eventually get to Lewis structures, I highly recommend it. I see this topic a lot with questions. A lot of students don't fully understand Lewis structures, which I completely understand. It's a different language pretty much. So yeah, I definitely recommend it. So check that out. I'll be placing the link in the chat, and then I'll talk about it again, either in the middle or towards the end, just so I know everyone's coming in at different times. Okay, so let's go ahead and let me see. Abby is stating, hey, do you have any advice for me? I have to take intro just to get into a program at any college, but my career has nothing to do with science. I really have to pass with a C, and I'm doing pretty bad, and we're on chapter 5 now. Tutoring doesn't seem to help me. Feel like I really struggle with numbers, also memorization. Any advice? Well, for the intro, I would say, let me know, by the way, Abby, what chapter 5 is on. Like what topic specifically chapter 5 is on, that'd be helpful. But something else that I've noticed, like if let's say you're struggling with numbers, really taking it piece by piece, and then even looking back at the specific type of algebra that maybe you need help with. So a lot of times students, if sadly, if algebra isn't, your strong suit, chemistry can be a little bit difficult. So what I would recommend doing is, since, you're also studying for chemistry, I also recommend studying for a little bit of algebra and going back to those basics and understanding that. Definitely let me know what chapter 5 is. I want to be able to help you out as much as possible. And then I'll also place a Oh, you just finished molecules and compounds. Got it. Okay. So molecules and compounds, that's not too math-based at the moment. It's really just like concepts. And yes, it is a little bit of memorizing. I'll go ahead and put some, we probably are going to do naming compounds. I'll place a video link of one of the videos that I did that's really helpful on naming ionic and covalent compounds. So that one I would definitely say to check it out. And then of course, if you still feel like you need additional help, that's what these Q&As are for. Ask your questions. I'm happy to help. So yeah, that's what I would pretty much say. I'm going to drop a link in the chat for the naming compounds video that can really benefit. You can really benefit from it. So I hope that helps. If not, definitely ask me more questions. Andres says, can you please explain mass to mass stoichiometry? Sure. So, and then as everyone starts to kind of come in, I do recommend if you have a specific question, like if you have like an example or whatnot, that speeds this up really a lot faster, really, and it helps me out. So if you have a specific question, make sure to put that in the chat. But for now, I'm going to answer Andre's question. Can you explain mass to mass stoichiometry? So mass to mass stoichiometry, when we're looking at this, we're really saying we're going from grams of one compound to, and I'll say compound A to some other compound B. And I'll grab a question right now. So to some other compound B. So the main thing that we have to focus on is something known as molar mass. So molar mass will act as your conversion factor. And then as I look for all of my little examples here, let me grab an example real quick for stoichiometry. So this is known as stoichiometry, grams to grams. Okay. Here, let me give you an example. There we go. So let's say if we had what mass of H2O or water is needed to produce, and I'll say 3 grams of H2. Okay, so hydrogen gas. So we're going from grams of one compound to grams of a completely different compound. And then they will provide you with an equation. I'll provide that with you now, but they will give you an equation. Sometimes they will have you balance it. For now, I'm just going to give you the balanced equation because I want us to focus on how to go from grams of one compound to grams of a completely different compound. So this is O2. Okay, so this is our balanced equation. Now, our plan with this is going to be going from our original or given, which is that 3 grams of H2, since that's the only thing we have. So our plan will be going from grams of H2. And then since we're trying to get to H2O, which is a completely different compound, there's something known as a mole-to-mole ratio. What a mole-to-mole ratio does, it allows us to go from one compound to a completely different compound. So that's what I'm going to do here. I'll start off with converting grams of H2 to moles of H2. And then I'll get to moles of a completely different compound. So the first step is going to just be using our molar mass of H2. So our first conversion factor. And if you're new to kind of me saying conversion factor, what a conversion factor is, it allows us to go from one unit to a completely different unit. So I'm going to use the molar mass of H2 as my first conversion factor. And then I'm going to keep going. And then once we're finally at moles of H2, I'll use the mole-to-mole ratio, and I'll show you everything here. I'm just outlining our steps. Mole-to-mole ratio on our balanced equation. Okay, and so as mentioned, our mole-to-mole ratio allows us to go to a completely different compound. So this goes to moles of H2O. Now that we have that, there's one last step. Since we want to get to grams or mass, that means grams of H2O. So then lastly, our final conversion factor here, our third one, would be the molar mass of H2O. And then I'll set this up and show you how we do this all over again. So I'll start with the given, and our given is that 3 grams. I'll put that on top, so 3 grams of H2, and then we're going to multiply this by our first conversion factor. So our first conversion factor was that molar mass of H2. So using your periodic table, I'll look at how much our mass of H2. So our mass of H2, or really even of just one hydrogen, is 1.01. Multiply this by 2 since there are 2 hydrogens in this case, so that gives us 2.02. And then from here, I'll align the grams and grams so they can cancel. And then on top, this is per every 1 mole. Since our molar mass, by the way, is always grams per mole, that's the proper unit. And then that would be H2. I'll keep going. Our grams of H2 and H2 would cancel. Now we're left with moles of H2. So we're at this step. We're at moles of H2, and we want to use our balanced equation to get from moles of H2 to moles of H2O. So then I'll align, once again, the units so they can cancel. Moles of H2 on the bottom, and what I'm trying to get to is moles of H2O. So you're going to keep seeing this pattern where you're trying to cancel out your next unit to then get to something else, and then you're going to keep going until you finally get to your desired unit. So now I'll use the balanced equation and put the coefficients of our balanced equation right here. Okay, so I'm going to look back at our balanced equation, and for every 2 moles of H2O, there are 2 moles of H2. So that's where I'm getting my mole to mole ratio, is just from my balanced equation. So I'll put a 2 here and a 2 there. And then we'll keep going. Our moles of H2 would cancel, and then now we have moles of H2O. And then lastly, I'll get to grams of H2O, which was what we wanted. Is this stoichiometry, Rory? Yes, it is. This is stoichiometry. This is going specifically from grams of one compound to grams of a different compound. And then continuing with this last step, we're going to use our our molar mass of H2O to finally get to our grams. So I'll put the moles of H2O on the bottom, and that's always 1 whenever we have our molar mass, and then put the molar mass of whatever water is. So let's figure that out. So here, this is for H2O now. The molar mass of H2O, this is 1.01 for just one hydrogen, times 2 since there are 2 in this case, so 2.02. And then we're going to add that to the mass of oxygen. So really we're adding 16 plus 2.02, which gives us 18.02 grams of H2O. Now that we finally have that, let's cancel out the units, and then we'll multiply everything out. So our moles of H2O and moles of H2O cancel. And then note that all of our other units canceled. We finally have grams of H2O, and that's what we wanted all along. So all we have to do now is multiply straight across, multiply the 3 times the 2 times the 18.02, and then divide by these 2 values multiplied. So I'll start there. I'll do 6, because that's 3 times 2, 6 times 18.02, and that's 108.12 on top, divided by, I'm going to do the bottom portion now. And we have 2.02 times 2, so really 4.04, and then I'll divide those values. And then from here, this will give us 26.76 grams of water. Last step is to check your sig fig count. So how many sig figs do we have? Well, initially we just had 3. Or sorry, we just had 1. There it is. The 3 was just 1 sig fig. So then I'll round this to only 1 sig fig. And then how I do this whenever I have like a larger value, and it's not like I can just make this 2 and that's the final answer, which it wouldn't be because that would change the value. So what I would do instead is just change this into scientific notation. So I'll move this over once, and that's now 2.676 times 10 to the first grams of H2O. Now I'll round up if I need to, which I do in this case. And then I'll look at that 6, round this up to really 3, and then this would be 3 times 10 to the first grams of H2O. That's if there was only 1 sig fig. That was mass to mass stoichiometry, and mass to mass stoichiometry for everyone, that's just going from grams of one compound to grams of a completely different compound. I'll answer the next question. All right, let me make some room. And then everyone that's joining in, you're welcome. Andres, you're welcome. Happy that helped. Everyone that's just joining in, If you have a specific question, like you have like an actual example, that helps me so much just to be able to like quickly move along with these questions. All right, so now I'm going to answer the next question. Let's see, the decomposition of N2O to N2 and O2 is the first order reaction. Okay, so I'll start off with just drawing or writing this equation first off. So this is decomposition. So decomposition means we're taking a compound and then we're going to really decompose or break this compound apart into two separate elements. And so that would be our first equation. I'm going to balance this real quick, and then I'll keep going with the question. So balancing this equation real quick, all we really need is that this oxygen has only one, yet this oxygen has two. So I'm going to place a 2 in front. So placing a 2 in front, now we have, let's check how many we have. So 2 times 2 will be 4. We have 4 nitrogen on this side, and then there's only 2. So I need to put another 2 here, and then that's finally balanced. So that's balanced for now. Let me keep going. So I believe this is kinetics, is a first order reaction. At 730 degrees Celsius, the rate constant, or K, is 1.94 times 10 to the negative fourth minutes to the negative first. If the initial pressure of N2O is, so our initial pressure is 3.50 atmospheres at that given temperature, calculate the total gas pressure after 1 half-life. Assume that the volume remains constant after 1 half-life, if this is first order. Sure. So for those of you that this probably doesn't sound familiar, this is the second half of chemistry. Or this is, if you're in an AP course, this is an AP chemistry course. So this is known as kinetics. Let me go ahead and grab the formula for half-life. And just because there are so many formulas, which you've probably already know that. Cool, I found it. Okay, so first, the fact that this tells us that it's first order, since it really has to tell us what order it is, since there are so many formulas. For half-life, our first formula is, this just tells us our half-life, and then this is 0.693 divided by our constant, that rate constant that's provided, so K. And that's what I'm going to do first. So they're asking, calculate the total gas pressure after 1 half-life. Pretty much so far, that's all we have to do. Let me double check. That's in seconds. I just have to change it to seconds, I believe. Yeah. Okay. So here they give us our pressure. Let me double check what else other information I need. Before I actually place that K constant, this is in minutes. We want this to be in seconds typically for half-life. So I will have to divide. Let me show you what I do with the K constant. So 1.94 times 10 to the negative fourth. That minutes in the negative first just means it's on the bottom. And then from here, what I'm going to do is change this to seconds on the bottom. So we think of 1 minute is equal to 60 seconds, and then now that's correct. So I'll just really divide this by 60 to get it in the proper unit. That's my first step. So 1.94, and this is negative 4 divided by 60. All right, so let's see what we get. This gives us, hold on, 1, 2, 3, 4, 5, 6, 7, I believe. 3.2 times 10 to the negative 7th. There we go. Seconds to the negative first on the bottom. Let me just double check that real quick on my calculator. 1, 2, 3, 4, 5. 2, 3, 4, 5, 6. 6. It's a negative 6. There we go. All right, so now that our K constant is in the correct unit of seconds on the bottom, I'm going to keep going with this question. So it does give us our initial pressure and our temperature. It tells us that volume remains constant, calculate the total gas pressure after specifically 1 half-life. I'm just going to double check that there's really nothing else that I need to do. The fact that you're just solving for that gives you your K constant. So far, it seems like that's essentially it. It'd be different if they gave you, I'm just looking at all my formulas that I have, be different if they didn't give you the K constant, but no, it's as simple as plugging in now. Yeah. So really all we need for this, I know they provide you with extra information. You don't need it. I hate when they do that too. But the main thing here is you just had to change that K constant, that rate constant, to the proper unit in this case, which is seconds on the bottom, and then knowing your formula, knowing the fact that it's first order, plug that in. So that's exactly what I'm going to do now. Now that it's in the proper unit, I'll plug this in, and then I'll put this 3.2 times 10 to the negative 6 seconds on the bottom, and then finally just divide, and that will give you your half-life. So let's see what that gives us. 0.693 divided by 3.2 to the negative 6, and then that gives us a large amount, so 216. I'll change this to our scientific notation. This is seconds on the bottom, so changing this to scientific notation, 1, 2, 3, 4, and 5, 2.165, and then I'll put the rest, times 10 to the 5th, and this is seconds on the bottom. So the main thing with that question was, this is kinetics as mentioned, the main thing with that question was just the fact that you needed to change the units from minutes on the bottom to seconds. And then how we did that once again was just dividing by 60 seconds. And then from there, knowing your formulas, knowing your half-life formulas, this is specifically for first order. There are different ones for 0 order and second order, so definitely watch out for those as well. Other than that, there was nothing else that we needed to do. And all right. And then just to let you guys know, I do have formulas, a formula sheet. At this moment, I don't have the second half of chemistry. I just have the first half of chemistry formulas up there, but I am working on the second half of chemistry as well. For everyone who is in the first half of chemistry, I do have a formula sheet for you guys. So if you fill out this form specifically, you can get that formula sheet emailed to you, and I really recommend it. It has all the formulas you need to know this entire semester. Moving on to the next, and the link will also, by the way, the link will also be in the description box after this live session. Okay, so let's see our next question. So Anisha says, I struggle understanding organic chemistry. Can you please help me? Anisha, if you have a specific question on, like, is it naming? Is it reactions? What specifically on organic chemistry can I help you with? What are you guys working on? Definitely let me know. As always, guys, if you guys have a specific example or a specific question that helps me know where can I help you. I absolutely want to help you guys. I just want to know, what are you struggling with? Okay, I'm going to go into another question. What are the differences between condensed, empirical, and molecular formulas? Okay, so let's go ahead and show those different differences. And then by here, let me grab an example just so you can see the differences real quick. Let's see. Okay. So first type, I'll start off with just a condensed formula. A lot of times what a condensed formula is, like let's say if we already had, and I'm going to draw a Lewis structure real quick, or just a structure in general. This is known, if this draws, come on, there we go. So this is a Lewis structure. This is just a glimpse of that, but I want to emphasize on what a condensed formula really looks like. So what a condensed formula looks like is just if they give you a structure and they told you to find the condensed formula for this, then from there you would count how many of each element there are and then put it in that sort of specific formula. So like in this case, a condensed formula would have been carbon, since there's only one carbon, and then let's count how many hydrogen there are. Well, in this case, there'd be 1, 2, 3, and 4. So then I'd put a subscript of 4, so this would be known as a condensed formula overall. With the condensed formula, what you're really looking at, by the way, is it's pretty much just the sense that they give you a structure initially, they ask you to find the condensed form, and you're just counting up how many elements there are of each, and that would be representing your overall condensed formula. When it comes to something being empirical or molecular, that changes a tiny bit. So let's say if we had something that was more like empirical, what I want you to think with an empirical formula, it's like a rough guess or like an educated guess. It's an estimate of how many elements are actually within that compound. For example, let's say if we had, and let me see if I can think of it this way. The simplest one I can possibly think of is water. We pretty much all know the molecular formula for water. It's H2O, right? So this is our molecular formula for that. Molecular formulas are exact. We know exactly how many elements, how many hydrogens are within a water molecule. We know exactly how many oxygen are in our water molecule, right? So that's what molecular is. It's just exact. But empirical, our empirical formula is a guess. So let's say I didn't know what the formula was for water, but I knew that for sure we had an oxygen, and I know for sure we have a hydrogen, but I don't know how much of each. I'm going to say there's one of each. I don't know. I'm not sure. So that empirical formula is just a guess, trying to figure out, I don't know how many there are exactly. I just know that there are there's at least a hydrogen and an oxygen. But then molecular is stating the exact amount of each element, and it's a specific think of it, it's the exact answer. And then empirical, it's like a guess. Hope that makes sense. And then condensed was just going back to them giving you a structure and you writing how many elements there are of each when you're looking at that structure. Moving on. So Charlie, that was your question. I have Ashanti asking how to find the formula names such as, okay, so let me write that formula name for you. And then this looks like a polyatomic atom. Let's see what we got. So ClO to the negative fourth. I think that 4 should be on the bottom and the negative on top because that's a specific case. There we go. Okay, so this is a specific form here. And then, by the way, on my formula sheet that I mentioned, I do have all of the polyatomic atoms listed. So this is actually a very common polyatomic atom. So like if you're trying to figure out, let's say the formula name for this, sadly, this one you have to memorize. There is no trick to this. This is known as a polyatomic atom. What a polyatomic atom is, it's just stating that we have multiple atoms or multiple elements kind of like fusing together or coming together. And that's why you see that we have a certain amount of chlorine, and then we have several oxygen in this case, all linked together. It's a polyatomic atom, or in this case, polyatomic ion. Ion just meaning it's negative. It has a negative charge. So any type of atom or ion, just means that it's an element with a charge. So in this case, this does have a very specific name. It's known as perchlorate. Let me make sure I'm spelling that right. Chlorate. There we go. So this is just one to have memorized, to have that down. I do have, as I mentioned, I do have a formula sheet that has all the ones that are really common for you to know. So definitely sign up for that. I really placed that in the chat and it will be in the description box at the end of this live session. But that would be the answer for the specific case. And then Juliana asked, writing chemical reactions from words. And we have a question. Okay, so let me answer that next question. So our question states the explosive reaction between hydrogen gas, and so I'll say hydrogen gas, and then we also have, I believe, another gas, and oxygen gas. And oxygen gas forms water vapor. Forms water vapor, H2O. Okay, so H2 gas and then oxygen gas, and oxygen gas forms water vapor. Okay, so with this type of question, something to note is something known as diatomic atoms. What diatomic atoms are, it means that they exist in two. So they exist in pairs. Anytime we see like hydrogen gas or oxygen gas, it's not just going to be H, it's actually going to be known as H2. That's what I mean by something being diatomic, is because di means two. So hydrogen doesn't want to be alone, it wants to have a buddy. So that has to be H2. And then plus oxygen gas is also diatomic, it's O2. And then it's stating that that will form or produce water vapor, or really just water. So I'll also state the states here. Since these mention that they're gases, I'll put that a G there just to state that it's a gas. And then this next one says it's water vapor. The fact that it's vapor means it's also a gas. So they're all gases in this case. And then something else to just kind of note, and of course, I'll balance this in a second. But diatomic atoms, the ones that you for sure know and how I personally remember them, it's kind of strange, but how I remember it is CHON, and it's the halogens. So that's how I learned it, and that's just what's always stuck with me personally. But CHON just refers to carbon. That's going to be diatomic. Same with hydrogen, oxygen, nitrogen, all of your different halogens like chlorine, fluorine, iodide, bromine, and so on. So those are all the different ones that will exist in two. And your other hint here was the fact that it stated that it was a gas. So anytime any of these are stated that they're gases, they will be diatomic. It also has to do with, like I mentioned, in like the universe and in chemistry, they're never going to exist just by themselves. So that's something to note. And then let's go ahead and, since we got that down, let's go ahead and balance this out. So let me scooch this. Let me see if I can scooch this over. Okay, I'm going to balance out this overall reaction, and then we'll answer the next question. So let's see. Okay, so I'm going to write out every single element and see how many of each there are. So there's hydrogen, oxygen, and same on the opposite side. So then I'll place how many hydrogen we have, which is 2 on the reactant side, and 2 oxygen also on the reactant side. Now let's look at hydrogen on the product side. Here's 2, and oxygen has 1. So then the only thing that isn't balanced is oxygen in this case, because this side has 2, but the other side does not. So I'll place a 2 in front of the water, and then now this is like it's going to distribute. So 2 times 2 with our hydrogens will give us 4, and then 2 times this 1 oxygen will give us 2. We're still not balanced. Our oxygens are balanced, but hydrogen no longer is. So then the last thing to do to make this into a 4 is to place a 2 in front of that, to make a 2 there for our coefficient, and then to continue on. So 2 times 2 would give us 4, and then this would be 2. There we go. That is our balanced reaction. That is done. And so that was Juliana's question. Hope that helps. As mentioned, those diatomic atoms I think are a tricky one, so definitely know those. Next question. Let's see what we got. Okay. First up, the next question is asking, how can you tell if a solute is volatile or non-volatile? Okay, so if something is volatile, really, it means that it's going to evaporate very quickly. Something that is non-volatile means it's not going to evaporate very quickly. So it does depend on its state. I would also say there's a lot of factors to this. One, if it's like a gas state, then yes, it has the ability obviously to evaporate. Now, there are specific solutes that evaporate quicker than others. So that does depend on, let's say, like boiling point. That's something to mention. Boiling point is the main thing that I would see you looking at if you've looked at that already. So like the ones that I can instantly think of that would evaporate very quickly and be volatile would be something like ethanol or acetone. Those are common solutes that, oh, I'm sorry, not solutes, those are solvents. Did you mean solvents? Sorry, I think you meant solvents. So there's 2 differences, by the way. A solute would be something that's like more in a solid form, Like if I were to make, I'll do this real quick. Like if I was to drink some iced tea, like some iced tea with sugar, if I were to put sugar there, that would be our solute. So solute is whatever is being dissolved, and then that liquid that is doing that dissolving is our solvent. So typically, I believe it should have been solvent, but as mentioned, it's whatever has a, I would say whatever has a lower boiling point, because that means it's easier to evaporate. So that's the main thing to focus on is boiling points. So whatever's lower will be able to evaporate quicker. Whatever's higher won't. I hope that answers your question. And then I'll move on to Evelyn's question. Could you go over mass percentages? Sure. All right, so with mass percent, there's a specific formula for this. Here, let me go ahead and give you the overall formula. So mass percent, what I want you to look at with mass percent, it's going to be the grams or the mass of whatever we're looking for. So it's an individual element typically. So like let's say grams of, I'm just going to say the part that you're looking for. And then you're going to divide that by the whole or the entire compound's mass. And then from there, you'll multiply this by 100 since it is a percentage. Okay, so let's say if I were to give you a question and it was find the, I'm going to say the mass percent of, and I'll give you, trying to think of an equation real quick. Let me see if I can grab one. There we go. And let's say of iron, of Fe, find the mass percent of iron in iron oxide, something like this. Okay. So if they were to provide you with something like this, then what you would do is going back to our formula, we want just the grams of the part that we're looking for. So what's the part that we're looking for? Well, they're asking us to find the mass percent, or really, you know, the main thing that they're focusing on is just iron itself. So the grams of iron is the part that you're looking for. So we'll look back at our periodic table and figure out what's the molar mass of iron in this case. So that would be 55.85 grams. And then now this will be divided by the entire mass of our compound. This is our whole. So then we have to figure out what the mass of the molar mass of this iron oxide compound is. So let's do so. So iron we said was 55.85. We'll multiply this by 2 since there are 2 irons in this case. And then next I'll have the oxygen. There's 16 times 3 since there are 3 oxygen. And then we'll multiply everything and then add everything together. So 55.85 times 2. That gives us 111.7. 16 times 3, I believe, is 48. Yes. And then I'll add those two together. All right, so adding these two together, that would be that whole portion that we'll put on the bottom. So this is 159.7 grams. So that's what I'm going to put on the bottom. And then lastly, divide these two values, multiply by 100, and that would give you your mass percent. So this is what mass percent is then equal. As mentioned, it's just the grams of whatever part we're looking for divided by the entire compound, or it could sometimes be like the sample, or pretty much whatever entirely they gave you to begin with. And then you'll multiply that by 100. So let's do that math and finish this question up. So doing that math, I'll divide these two. So 55.85 divided by 159.7 times 100. And that gives us 34.97%. And then I'll round this up just to 35%. And this is of iron. So this is still the mass percent of iron within that compound. So that's what how you would find mass percent. And then let's look at our next question. Let me erase all this. Okay. Let's see. So, okay, isotopes. So we're going back to isotopes, and we're given the average mass of, here, let me look at our average mass. So we're given our average mass, and then of one element, and then let me write all of this information, 151.965 atomic mass units, AMU. And then if 47.8% of our first isotope is given or found, and then I'm actually going to write the specific mass that's provided, 847. All right. What is the mass of the other isotope? Okay. So this is so far what we're given. The main thing is to know the formula, of course. Now, since we're asked to find the mass of the other isotope, what I'm going to do first before I set anything else up, the fact that this already gives me my first percentage, we can figure out the percent of the other isotope by subtracting this first percentage by 100, since this is all out of 100%. So I'll do that first. So my first step is just to take 100%, subtract that from the 47.8, and then that'll give me the percentage of the other isotope that we're looking for. Because with these types of questions, you only have to have, like, you can only have one unknown, or else it's impossible to figure it out. So let's see, there's 100 minus 47.8. That gives us 52.2%. So that's the percentage of our second isotope. And that's very important. Now that I have that, I'm going to place this in the proper formula for percent abundance or average mass. So what this is going to look like, it's going to be the average mass of an isotope, and then this is going to equal our percentage times the mass of that isotope that's provided, plus however many isotopes we had in this question. So since we only had 2, that's why I'm only using 2 of these values. However, if we had 3 or 4, I would keep adding and keep going the same way, but there's no need in this question. Okay, and then let's go ahead and plug everything in. So what we have initially, they gave us the average mass right here, so I'm going to plug that in. That was 151.965. And then we were given the first percentage. So our first percentage was 47.8. Now we have to change this to a decimal. And I know it already technically is a decimal, but we have to get it out of that percentage form. And how we're going to do this is by dividing by 100, or what you can really do is just move the decimal place over twice to the left. So that's what I'm going to do. I'm really just dividing this by 100, moving this over 1, 2. And then now our percentage is 0.478, and that would be the proper form. Yes, you do have to do this for every single percentage every time. And then now I'll multiply this by the given mass of the first isotope, which is 150.919847. And then I'll add this, running out of room here, but I'll add this to the other percentage. So for the other percentage, we had 52.2%. I'll divide this by 100 once again and move over that decimal place. So moving this decimal place over to the left to 1, 2, this gives us 0.522 times, and I'm going to say x. So instead of that multiplication sign, or that typical multiplication sign, I'm just going to put the other multiplication symbol and then put an x, since that's what we're looking for. We don't know what that is. So before doing anything else, I'm just going to multiply this first little portion here. So this is what I'm going to start off multiplying with, and then we're going to use algebra to solve for x. So there's 0.478 times 150.919847. That gives us 72.13968. And then I'll add this to, let me go ahead and bring this closer. So this is 0.522, and I'm just going to say x. That's what we're solving for. You could even drop the parentheses now, since you already did what was in parentheses, so that's totally fine. And then I'll set this equal to the mass that we had initially, that average mass that they gave us. Okay. So I know I'm running out of a little bit of room, but we can kind of see it. But the main thing that I want you to look at is we're going to combine like terms. This is going way back to math, I know. But combining like terms, I'll subtract over that 72.13968 to both sides, and then we're going to solve for x. So this cancels. Let's see what this gives us after we subtract. So subtracting these two values, we'll get 79.825, and that'll equal, let's see, we're still going to have that 0.522x. Okay. Last step, pretty much. All right, finally, I'm going to divide this over that 0.522 just to get x by itself. Since both of these are being multiplied, we'll do the opposite operation. And I'll divide those two values. After I divide these, x, or our other mass, would be, let's see, 79.825 divided by 0.522. So this is the mass of our second isotope. And that would be an AMU. That is your final answer. So that would be it for your final answer. That's what you would do in this case. Let me see if I can put a link to one of my videos. I did several examples similar to this. So, and they're actually really good test questions. Hint, hint. It's an isotope video that I did. I'll put that in the chat just to help you out, Abby. So yeah, definitely check that one out. I recommend it. There's two specific different cases that I mentioned, and I've often seen them as test questions. Okay. And by the way, just to let you guys know, everything that I do, like all of my videos and all of the workshops that I'm doing, the questions that I put are common test questions that I've just seen over the past 10 years of tutoring. Teachers like to recycle their questions. So that's just something that I like to share with you guys. So, I mean, let's all, sharing is caring, right? So to make it easier on you guys, these are just, like I said, they're common test questions that I always see. So that's what I always put in my videos. Okay. Let's erase all of this. All right, let's move on to the next question. And what do we got? Okay, so Evelyn states, what resources did you use to study for chemistry during college, specifically general chemistry? You know, resources, sadly, I didn't have as many as I wish I did. A lot of times what I did was I formed study groups, and even then I didn't really feel like that was the best for me. The main thing I would say is, because I didn't like my books, I find this even now still tutoring, the chemistry books aren't designed for students, unfortunately. Why do they do this? Trust me, I wish I knew. But that's why I come in pretty much. That's why I've become this resource for you guys, because I wish I had those resources growing up, and just going in, you know, when I was in chemistry struggling, I wished I had someone guiding me and telling me what should I look at? How should I study? How in the world do I even do this? So that's why I've provided so many resources. So Evelyn, I'd be happy to be your resource just to study. You know, I have all these different videos. I've been working, I don't know if you heard that I've been doing, I have a new workshop that I just made for you guys. And it's on Lewis structures, and I'm going to be working so much harder, even more, to have so many workshops up for you guys. So that's something, if you guys are just tuning in, I have this resource for you. I really put a link in it, and then of course I'll put it in the description box after this live session. It's at this very moment, it's only $10. It's on pre-sale. Don't know for how long, and then it will go up to $20 maybe in a couple weeks. So what this is, it's just a Lewis structure workshop that I've designed, and think of it like it's absolutely everything you possibly need to know for Lewis structures at a very discounted price. And it even includes notes, my notes that I've made for you guys. So as I mentioned, I know how weirdly worded the books can be and complicated. So that's why I want to actually translate it and make it into English. So that's what my notes are. So they make more sense. Okay. So that's something that you also get. And then of course I do have that free resource for you with the videos and this Q&A, plus the formula sheet that I mentioned before that you guys are always welcome to sign up for. So that's what I would recommend. Let me continue with the questions. Let's see, our next question, there is 24, let me write that down, 24.8 grams of an unknown molecular solute is dissolved in, okay, so this is dissolved in this is a longer question. In 5.39 moles. Oh, okay. I really see what's coming. In 5.39 moles of our unknown, actually not our unknown, causing the freezing point of pyridine to decrease by sorry guys, let me just write this question down. Celsius, calculate the molar mass of our solute, find the molar mass, and then for the pyridine, the molar mass is that amount. Okay. Okay, so we have the molar mass, and I'm just going to say mm, that just means molar mass, of our pyridine, which is this. So 9.10 grams per mole. We're given our freezing constant, which is known as Kf, 4.26 degrees Celsius divided by molality, which is small m. And then they're saying calculate the molar mass of our solute, and then we know our... what do we know? Causing the freezing point of pyridine to decrease by 3.79. We have that amount. Okay, so I'm going to go back to the formula of freezing point. And what that is, it looks like this. So if that's our freezing point depression formula, then this is molality and our Kf. There we go. So we're really given our Kf. And then we don't have the molality in this case. And I believe they give us one more thing. They tell us causing the freezing point to decrease. All right, so they give us enough. The first step is going to be solving for molality. So solve for molality. Remember what molality even is. This is different from molarity. This is the moles of our solute divided by the kilograms of our solvent. All right. And then what I'm going to do first is I just want to figure out the moles of my solute by plugging everything in. So they give us our freezing point depression, and that's that decrease. That's that 3.78 degrees Celsius. And that's then going to equal our Kf, or our freezing point constant. So 4.26 degrees Celsius divided by m, which is just known as molality. And then I'll also figure out what in the world molality is in this case. So all I have to do is divide entirely by that value. So I'll divide by 4.26 on both sides. And then that will give me my molality, and then we'll keep going from there. So this would be 3.78 divided by 4.26. And that gives us 0.887, and this is specifically our molality. Now, as mentioned, the molality was the moles of our solute divided by the kilograms of our solvent. And then from here, they gave us other information. They told us that we had exactly 24.8 grams dissolved, of our unknown solute is dissolved in 5.39 moles of... Okay, so that is our solvent. Let me just double check what else I can get from this question. They give me my molar mass, and there it is. Okay, there it is. That was my missing piece. Okay, so we want the molar mass of this, right? Now, we have the solute. We also want the grams, really, is what I'm trying to say here. So since we want the grams specifically of our solute, because later on we're going to get to grams divided by moles, since that's what molar mass is, I have to figure this out. So what I'm going to do, pyridine, by the way, let me go a little step back. What they gave us our grams, right? Dissolved in a certain amount of, this is our solvent, because that's what's being dissolved into something else. Whatever is doing the dissolving is your solvent. So then what I have to do is I have to take this given amount of moles, and then they also provided us with our molar mass of specifically this compound. So I have to multiply that. So that's what I'm going to do now. I'm going to take there we go. Okay. Well, I'm going to take that 5.39 moles and then multiply this by the molar mass to get the grams. So they gave us the molar mass. I'll put the moles on the bottom, And then on top, I'll put that 79.10 grams. And by the way, this is still of pyridine, which was just what they give us. Okay, we'll multiply these two together. And this is 5.39 times 79.10. This gives us 0.068 grams. And then from here, remember we want our kilograms of our solvent. So what I'll do next is, using the metric system, change this to kilograms. So this is in grams now. So then now what I'll do is, this is really 10 to the third, since that's what kilo is, grams, and this is 1 kilogram. Multiplying those two, or dividing those two really together, let's see what we get. So dividing by essentially 1,000, this is 0.0000. I'll change this to scientific notation in a second. 142. Yes. So changing this to scientific notation, 1, 2, 3, 4, and 5, 6.8142 times 10 to the negative fifth kilograms. Almost done with this question. All right, so this was our grams of our solvent. Perfect. Okay, continue with this. So hope you're still with me. Now, since that was our kilograms of our solvent, I'm now going to take our molality that we just got previously. Okay, so our molality was, let me go back if I can to what we had. There we go. All right, stay with me. So there we go. So our molality was that 0.887 moles of our solute, divided by, we don't know how many, it's really just 1 kilogram of our solvent, since that's the proper unit for molality. And then now I'll multiply this by the grams of our solvent. And the reason why I'm doing this is so those grams and our grams of our solvent will cancel. And then now we're just left with the moles of our solute. So then once I'm done doing that, and let's see what that gives us. So multiplying these two together, this is 0.00060 and 4. And then, like I said, I'll still move this back. So 1, 2, 3, 4, 5. This is really 6.04 times 10 to the negative fifth moles of just our solute now. One more step. So the last step is going to be finding the molar mass. They gave us initially the grams of our unknown solute. So we only want the molar mass of our solute. That's what the question's asking. So we want the grams divided by the moles specifically of just our solute. So we have the moles of our solute. That's what we found. So I'll put that on the bottom. And then what they give us initially is the grams of our solute. So that 24.8, that's where that comes in. And then once we divide these two values, we are finally done. I know this question was very tricky. You have to kind of like be strategic and think about how in the world am I going to get just the solute itself. So after we divide these two, it's -5. All right, this will give us 410,596 grams per mole of our solute. And that would be our answer. We can change this to scientific notation again. This would be 1, 2, 3, 4, 5, 4.10596 times 10 to the fifth grams per mole. And then lastly, how many sig figs did we have? We had 3 sig figs initially, so I'll round this up right here to 3 sig figs, so 4.11 times 10 to the fifth grams per mole, and that's our final answer. That's our molar mass of our solute. Okay, let's see what else questions I got with my time remaining. So that's done, and Juliana asks okay, so a single replacement question. Sure. These tend to be good. Okay, so we're still building different reactions here. The question states a piece of aluminum. So a piece of aluminum is dropped into calcium acetate. Okay, so what I want you to think of, what they just mentioned here, are only our reactants. So they tell us that a piece of aluminum, which must be in its solid state, is then dropped into a solution, which must be aqueous. So calcium acetate, this is going back to naming compounds and knowing all of our different polyatomic atoms. So here, Calcium has a 2+ charge. Acetate, that's a type of polyatomic atom, which is C2H3O2 with O2 with a negative charge. And then what I'm going to do is make sure that our charges are balanced. So I'll place a 2 there. And then this is really going to be calcium, parentheses. This is acetate. All right, let me go back. That's a 2. This is acetate, and then O2. And then we'll also put a 2 subscript on the bottom. And then what this would form, really with single replacement reactions, all that's happening is that we're going to swap our metals. So instead of calcium being here, for our product side, the aluminum will now switch and combine with this acetate, and then calcium will be on its own. So I'll show you what to do here. Really, it's these two that are going to combine to form our new product. So going back to the different states or the different charges, aluminum has a +3 charge. And then we said acetate has a -1 charge. So let's balance this out. By the way, this 2 out here does not come down. That 2 was only placed there, that 2 subscript was only placed there to balance out this entire acetate compound with calcium. Okay, so that's the only reasoning why this 2 is there. Now let's go ahead and balance these charges out. So placing that 3, that's going to lasso down, and this is how we'll write it. So this will go down. This would be aluminum, and then this would end up giving us a 3 on the bottom. So here, let's write that, then we'll balance. So aluminum, acetate in this case, 3, and then now plus calcium. Okay, and then I'm just going to double check one thing, because sometimes with these types of reactions, there could be no reaction, and that depends on something known as the activity series. If it is, I'll go into that. Calcium and aluminum. We can swap high to low. Let's see. Just double checking that this is a possibility. So aluminum, calcium, we're replacing aluminum with calcium. That's fine. This is fine. So you might have gone into something known as activity series. If not, don't worry too much about it, but that's what I was just checking right now to make sure that this reaction does work. And I'm going to keep going with this. So this is what our setup would look like. And then let's just make sure that everything's balanced, because it is not. So then balancing this chemical reaction, balancing this out, this is aluminum on one side, calcium on one, acetate on the other, and then any sort of polyatomic that remain the same on either side, I'm going to leave them the same when I'm balancing this out. It just makes it so much easier to balance. And let's keep going. So aluminum on the left side only has 1, calcium has 1, and acetate has 2. And then aluminum on the right side has 1, calcium has 1, and then acetate has 3. So the only thing that is not balanced whatsoever is our acetate. So what I'm going to do is I want you to think of this as kind of like making it into a common factor or common denominator sort of example with this. So like 2 and 3, what's our common factor? 6. So if I were to try to make the acetates on either side be 6, that's what I'm going to attempt to do. So if I were to place let's say a 3 here, and then now if this distributes in, this is going to multiply with the calcium, and there's 3 now. And this really only multiplies with this 2 on the outside, since we're leaving the acetate polyatomic ion intact. And then this just gives us 3 times 2, so 6. And then aluminum is still the same. We didn't change anything. And then on the opposite side, I want to make this into 6 as well for our acetate. So I'll place a 2 in front. And then distributing that in, once again, this is going to multiply with that 3. So for aluminum, there's 2, and for acetate, there's 6, and calcium remain the same. So finally, all we have to do is balance out the aluminum and the calcium. So aluminum requires 2 on the product side, and so we're going to put a 2 on the reactant side in front, and then calcium, there's a 3 on the reactant side. We're going to put a 3 on the product side, and that is our balanced equation. So that's what we would get. And that would be our final answer. Okay. Charlie just stated, I have an exam tomorrow, but wanted to say you have helped me so much. Your lessons are clear and easy. That is everything chemistry is not. I'm a 49-year-old student. Better late than never. I agree. Better late than never. Charlie, I encourage you to keep going. Really, I've been tutoring for a while, and I've actually had several students who are going back to school. I have several mothers who are they're closer to retiring than anything else, and they have even told me that, I wasn't happy with what I was doing, and I decided I wanted to be a nurse. I wanted to continue going back to school, and now it's actually awesome to see them in nursing programs and, where they want to be in life, and they're just happier. So yeah, I completely agree. Better late than never, because I would hate for you guys to not truly see what you're capable of and not truly, accomplish what you want to do in life. So I encourage you to keep going, and best of luck with your exam. I'm happy that, I can help in any way possible. Keep going, really. And so that was the Q&A portion for this part. I wanted to kind of just reiterate everybody who's like trickling in or came in maybe a little bit later. So currently I have a workshop that I'm doing that is already launched, and it's on Lewis structures. Really awesome workshop. Definitely check it out. I've already placed a link in the chat. There's also a link in the description box after this live session. It's currently on pre-sale. It's going to be for $10, and that is half the price of the typical cost that it would be. It's going to go up later on, maybe in a couple weeks. It's going to go up to $20, which is the original price that I will have it for. It's about, goodness, it's like, I want to say, think of it like 2 hours or more of tutoring, of uninterrupted tutoring. And it's beautifully designed. Really, I really encourage you to check it out, because I know how difficult Lewis structures can be. If you're currently not on that section right now, then I would say to still get it during the pre-sale value of half off. Just to kind of clue you in, I know how expensive tutoring, one-on-one tutoring can be, and I just wanted to have something that is affordable to everybody, because I know I know what it's like to be a college student. I went through it myself, so definitely check it out. Like I said, I'll place that now in the description box after this session. You can go into it already, just to kind of let you know the course. I'm still editing certain parts. So for this workshop, I'm still editing certain parts. So I'm going to be uploading every single day. There's already some videos that are uploaded. The notes are already there for you to access and download. So like I said, the workshop also comes with notes, very, very detailed notes that I have designed, and I just personally think it's so much easier to understand. So if you personally like the way I teach and like the way I explain things, I put that in an entire workshop. I also put that in on paper and put that on notes, showing you different diagrams as to how to draw Lewis structures, how to understand polarity, giving you different examples, and just giving you as much information, pretty much just the main information that you need to know without all of this chemistry nonsense, right? This translation of what is this? So yeah, that's what I definitely recommend. I'm putting that in the chat right now. Definitely check it out. And of course, thank you so much for being here. Let me answer. I have a couple questions here so far. I'm done answering some chemistry questions, but Lucy says, hey, I'm Lucy. I had an exam Friday and your videos helped me so much. Thank you. Awesome. You're very welcome, Lucy. I'm so glad that my videos can help and that I can help you in any way. I think that this is the most beautiful part of like the internet and YouTube, having this capability and this opportunity to be able to help so many students all around the world. Like, just to kind of let you know real quick, like I've always wanted to like help people. And that's always been something that I care so dearly about. And once I started teaching and just tutoring overall, I wanted to help hundreds of people. And now with YouTube, I get to help thousands of people, which to me is just the best feeling. So you are so welcome. I love helping you guys really know that. It's such a beautiful thing to be able to guide you and to help you just not be confused. Like I said, I wish someone was there for me when I was going through chemistry. So that's why I became this person and this guide. I also have Andres saying, thank you, Melissa. By the way, you should be my teacher in school. I really wish I could. For now, YouTube University. There, I'm a professor, but yay. And then Andres also says, do you give anything about physics? So I don't do physics. Currently, right now, I'm just focusing on the first and second half of chemistry, and then possibly later on math. That's what I've specialized really in. I got my degree in chemistry, and then, as you know, math does fall into chemistry, so I teach all the way to calculus. So that's what I do privately, but at this moment, I'm not offering that. But sadly, at this moment, no, physics is not something I teach, but I am here for chemistry. So with that, thank you everybody for joining. Definitely check out the workshop if you get a chance. And I'll definitely see you next Sunday, same time, 12 p.m. Pacific time, here live on YouTube. I typically enter the live a little bit earlier, like 5 minutes earlier, just to catch you up on what I'm doing, to get to know you guys a little bit better. So definitely be here next Sunday. Thank you for being here, and check out any new videos that I'm about to launch, and definitely check out that workshop. So have a blessed day today, and best of luck with everyone that has exams this week. Keep going. I'll see you guys next Sunday.